Good morning again. Now let us consider in this case those are the equations we have discussed in the last lecture, right? And we have discussed what is the natural convection, what are the advantages and the disadvantages of natural convection. So let us take the analysis further of this. Now, which momentum equation is more relevant in this case, right? So the y momentum along which the flow occurs and the boundary layer develops, right? So this y momentum equation is more important for us than the x momentum equation. And if you see in these equations, we haven't taken the rho out and rho out of the picture. Why? Because this rho here is a function of temperature. Because due to the temperature difference, the density difference occurs, and due to that density difference, the buoyant force or the natural convection takes place, right? And if I draw this is how it happens, right? Now if you see that here this can be neglected in both the equations, right? And in the x direction you can also neglect this pressure, but you can't neglect, now this is y, right? Y momentum equation. And the temperature, this can be neglected in energy equation. Now in this energy equation is directly linked with the momentum equation. In this, what we do in the forced convection, we solve the momentum equation for the V, we put that V value in the energy equation to get the value. But here this energy equation is somehow dependent upon this momentum equation. This has a direct role in this because this rho is a function of temperature, right? So for this, what we have to do? We have to do the boundary layer analysis. Right? And to solve this, we have to simplify this equation. So to simplification, we take the Bosniak approximations. It is a scientist which has given the approximation which says that this density variation with the temperature is important only for body forces terms, but not for other terms, which means that we can write this continuity equation taking rho out as a constant. We can write as du by dx plus dv by dy is equal to 0. And if this density is infinity, right, at this point, if you talk, then this change in pressure at this point will act as an hydrostatic pressure, right? And this can be solved by simple Euler's equation, right? And as you know that the hydrostatic pressure is equal to this, right? Sorry, the row is here, so we can't take this row here because that row will come down, right? So we'll replace this value here, right? And this equation now will become, it is rho u du by dx plus v dv by dy is equal to mu d square v by dx square. It will be rho minus rho into g. Right? Now by Bosenic equation, by Taylor's expansion, Taylor series expansion, we can write as rho infinity plus d rho by dt at infinity plus higher order terms, right? So here we take the volumetric expansion coefficient, that is beta, which is 1 by volume, is change in volume with respect to temperature at the infinity, which can be written as rho infinity d 1 by rho of dt at infinity, right? And we can write this beta as minus 1 by this of d rho by dt at infinity. Why? Because this can be written as 1 by rho infinity square of d, right? The differentiation of that. So from here we can write that dp by dt at infinity is minus of rho infinity into beta, right? So this rho can be written as rho infinity. If I put this value here, this can be written as minus rho infinity beta of t minus t infinity. So this rho infinity minus rho into g will be rho infinity g beta of t minus t infinity. And if I replace this value here, right, then I'll get as let me write the y momentum equation now. So it will be the y momentum equation, it will be rho u dv by dx plus v dv by dy as mu d square v by dx square plus we can write as rho infinity. What was the value? That is rho infinity g beta of t minus t infinity, right? And if you see that we have incorporated this delta t instead of density difference, we are now focused to the temperature difference, right? And if I take this rho down, let take this as rho infinity, so it will be, this will cancel out. This can be written as mu at infinity, right? So this will cancel out and I left with this. Let us take the dimensionless quantity. So let us take u star as u by vc, right? v star as v by vc. We don't know what is vc, we have to calculate it. This x will be x by L, as here L is this length, right? This y star is y by L, and this theta is as this dimensionless number. And when I put these values here, if you do the mathematics, we'll get the Vc square by L is u star dv star by dx star plus v star dv star by dy star, which is equal to mu Vc by L square d square star by x star square plus g beta theta t w minus t infinity, right? And if I multiply by L by Vc square, so what I'll get? I'll get L by Vc square. Here I also get L by Vc square, right? So here it is L by Vc square. So this will cancel out. Here one Vc and one L will cancel out, right? So so if you see this, we are more concerned with this term, right? So let me just give this term a brief. This is what is G beta into L by Vc square. So I can write this as G beta Tw minus T infinity by, let me multiply by L square, so it will be L cube and divide by L square, right? So here we divide by mu square, so this Vc square will be at this point, and here we'll get the mu square, right? And if you see this is nothing but 1 by Reynolds number square, right? And if you see this is a new number which is called as the Greshkov's number, right? So we get this Greshkov's by Reynolds number square. So this term is nothing but it is the Greshkov's by Reynolds number the square. And if this value right, so this is what is Greshkov's number, right? If this value is greater than that of 1, then we said it is a natural convection. And if this is approximately equal to 1, then we call this as the mixed convection. And if this is like this, then we call it as an forced convection. And this ratio, this Greshkov's number by Reynolds number square, is called as Richardson number. Right? Clear? So let us do in the next. Now here in this lecture, the convections are of 3 types, right? Somehow in the gate examination or in MCQs, they generally ask what are the different types of convections. And generally students write there are only 2, that is a natural and the forced convection. But the correct answer is there are 3 types of convection. One is called as natural convection, one is called as mixed convection, and one is called as forced convection. The next lecture we'll do the order of magnitude analysis of these equations, and let us find what are the relations between these quantities, right? Now from this relations we can write that this Greshkov's number the power half is somehow equal to the Reynolds number, right? With this ratio, the Richardson, and this Greshkov's number is G beta of TW minus T infinity by L cube by mu square the power half is equal to the Reynolds number, which is VC L by mu, right? So from here you can get this VC value. The VC is what? We don't know where this VC stands, right? So this is your VC we're talking of. So this VC will be somehow equal to G beta delta T into L, right? This will be like this. And if you see this can be written as 1 by Reynolds number, and this can be written as GR by Reynolds number square, right, into theta, right? So and if you write the energy equation from here, it can be written as U d theta by dx plus V d theta by dy is equal to d square theta by dx square. So dy square is alpha by VCL, which is nothing but is a function of Reynolds number into Prandtl, right? So in the next video we'll do the order of magnitude analysis of this, and we'll try to find what are the relationships built during that analysis. Thank you.